Today we're going to talk more about the phenomenon of entanglement. Entanglement is actually not just a quantum mechanical phenomenon, but it is a much more general one. It's just not very interesting outside of quantum mechanics. In order to ease ourselves into it, we're actually going to start with a classical version of entanglement, which is a little bit easier to follow. Imagine that we have two marbles identical in every way other than their color, one red and one blue. We put these marbles in a bag and we jumble them up so that we no longer know which one is which, and then we dump them out without looking into two separate identical boxes that can't be told apart. The boxes are then given to Alice and Bob, who then leave and each go to their own respective homes. At this point, Alice opens her box and finds the red marble inside. Before Bob even opens his box, we know that the marble inside that one is blue. We know this because we started out with a red marble and a blue marble, and once Alice found the red marble, that meant Bob must have had the blue marble. This is the idea behind entanglement. Alice might live in Tokyo and Bob might live in Bolivia, but the moment Alice opens her box, she knows with certainty that Bob's box contains the blue marble. That was really hard to say. And in fact, Alice can know which marble Bob has even if Bob doesn't, because Bob might not have looked inside of his box yet. We would call the system of these two boxes entangled, because you don't need to measure the entire system in order to determine the state of the entire system. Alice can determine which box has a blue marble and which box has a red marble just by measuring one of the boxes, even if the second box is very far away. This scenario is an example of what's called maximal entanglement, because a measurement of one of the states completely determines the other with no ambiguity at all. It's also possible to have partially entangled states, which we can demonstrate by adding a third marble, perhaps a second red marble, as well as a third participant who we'll call Carlos. Before Alice looks inside of her box, she has a 2/3 chance of finding a red marble and a 1/3 chance of finding a blue marble, and she knows that Carlos and Bob have the same chances. Once she opens her box, on the other hand, if she finds a red marble, suddenly the chances for Carlos and Bob have changed. Now she knows that there's one blue marble and one red marble left, which means Carlos and Bob each have a 50-50 chance of finding one or the other. This time, Alice opening up her box doesn't provide her a full picture of what's going on with the other two. It does provide her some information, though. It allows her to update her prediction probabilities from a 2/3 chance to find red and a 1/3 chance to find blue for both Carlos and Bob to a 1/2 chance each. Carlos is in the same position as Alice because he also, it turns out, has a red marble. Bob is a little bit lucky, though, because if Bob looks inside of his box, he'll find a blue marble, which means he does know exactly what Carlos and Alice are going to find because there are only red marbles left. Nonetheless, this is not maximal entanglement because a measurement of one part of this system or of one of these states doesn't necessarily provide all the information about the rest of the system. Hopefully, I haven't really taught you anything particularly new so far. This kind of reasoning is typically developed alongside object permanence between the ages of about 4 to 7 months. But now we can use this framework to talk about what happens when we have quantum mechanical systems that are entangled with each other, what makes them different from this, and how this idea has sparked a nearly 100-year-old debate that, frankly, is still not entirely resolved. In order to set up a quantum mechanical system that exhibits entanglement, first we have to talk about how to actually create an entangled system. So if you think back to our original example with Alice and Bob and the blue and red marble, the creation of this state basically was that we started with a known set of marbles. There were two, one was red, one was blue. They were distributed randomly to the two participants, and each one can only show up once. So this initial constraint is what created the entanglement. For example, if we had a box of millions of marbles with different colors, and we pick two of them randomly and put them in boxes and give it to Alice and Bob, neither Alice nor Bob can really learn very much about the other one by opening their box, right? They know, all they'll know is that the other participant doesn't have the thing that they have, but it doesn't really narrow down the options very much. One of the easiest ways to create a condition like this in quantum mechanics is to make use of conservation laws. For example, consider the neutral pi meson. It's a particle composed of a quark and an antiquark. It doesn't have any net electric charge. It has about 300 times the mass of the electron, a little bit less. And it also has no spin. It's a spin-zero particle, which means it doesn't possess any intrinsic angular momentum. The neutral pi meson is unstable, and it tends to decay, and the only restriction on what it can decay into is that the conservation of energy, conservation of charge, conservation of linear momentum, and conservation of angular momentum must be satisfied. One of the most common ways for this to happen is for the particle to decay into an electron and a positron. They have opposite charge, so there's no net charge. They're much less massive than the pi meson, so we have enough energy to do it. And because the electron and positron have identical masses, it's easy to conserve the linear momentum. They can just go off in completely opposite directions from each other. And to satisfy conservation of energy, they just need to be moving fast enough so that the total energy afterwards is equal to the rest energy of the pion. The complication, which is what we're going to make use of, is the fact that electrons and positrons both do have angular momentum. They are spin 1/2 particles, which means if you measure their spin in any particular direction, you'll always get a total amount of angular momentum of h bar over 2. So in order for the angular momentum of the system to remain 0 after the decay, if the electron is spin up, if it has positive h bar over 2 spin in a particular direction, then the positron has to be spin down or have negative h bar over 2 momentum, and vice versa. Since the initial system had 0 angular momentum, the final system has to have 0 angular momentum no matter the direction we choose to measure it. In order to simplify this conversation, let's say that the electron is sent to Alice and the positron is sent to Bob. Each of them possesses a detector that can be used to measure the spin of their particle. And Alice and Bob have agreed ahead of time that they're always going to measure the spin of their particles in a particular direction. It doesn't really matter what that direction is, as we just established the sum of the angular momenta of the two particles has to equal 0 regardless of the direction that we pick. For convenience, let's just label the direction that they've agreed upon to be the z direction. It could, again, represent any direction at all. We're just calling it the z direction so that we have something to refer to it by. Based on what we just discussed about angular momentum, if Alice measures that the electron is spin up, that means Bob is going to have to find that the positron is spin down. Likewise, if Alice measures that the electron is spin down, that means the positron has to be spin up. It's the only way for their momenta to cancel out and be 0. Decay processes like this are random, so we should expect each of these outcomes to happen 50% of the time. You might think, okay, well that means we should be able to write down the wave function of the electron as 1 over square root of 2 times spin up plus 1 over square root of 2 times spin down. And we could do the same thing for the positron. This is actually not correct though, because we just established there are really only two outcomes. Alice measures spin up and Bob measures spin down, or Alice measures spin down and Bob measures spin up. But the way that we wrote down these state vectors, we have the electron having a 50-50 chance of being up or down, according to Alice. And independently of that, Bob has a 50% chance of finding his positron spin up or spin down. That actually leaves the possibility for Alice to find the electron as spin up and Bob to find the positron as spin up, or for both of them to find the two particles as spin down. That would violate conservation of energy because Alice and Bob would have measured that there is a total angular momentum of plus h bar or minus h bar after the decay, even though they started with 0. The electron and the positron states are entangled with each other, and therefore they can never be written independently of each other, because information about the electron also contains information about the positron, because if we measure the spin of the electron, we know what the outcome of the positron measurement will be. But we can write down the two-particle state of this system, and we know that there are two possibilities. One is that Alice measures her particle as spin up and Bob measures his as spin down, or the other way around. And we know that each of these should have a 50% probability, and so we can write the state vector down like this. A few things. One is that in this notation, Alice always comes first, because Alice starts with an A. Bob always comes second because Bob starts with a B. And if I were to add a third particle to this scenario, or create a new scenario with 3 particles, then Carlos would be third because Carlos starts with a C. So even if I don't explicitly write down that the left is the electron and the right is the positron, anytime going forwards that you see 2 arrows in this 2-particle notation, the first one always refers to the state corresponding to Alice, and the second one always corresponds to Bob. To address the elephant in the room, why this negative sign? Why would I put that there instead of a positive sign? It's actually really important, but we're not going to go into it in a lot of detail because we haven't really learned how to. The long story short is that if we had a positive sign there and we calculated the expectation value of the total spin of the 2-particle system, we would actually get something that's not 0. It's hard to explain intuitively why that's the case, and mathematically we haven't quite learned all the tools that we need to do it. So for now, you're just going to have to trust me. However, if we have a minus sign here, the expectation value of the total spin remains 0, which is what we're looking for. This is a maximally entangled state because a measurement of one of the particles constitutes a measurement of the entire system. If Alice measures that hers is spin up, then we know that our system is described by this part of our wave function, whereas if she measures that it's spin down, we know that we're over here, and likewise if Bob does the same. Hopefully the previous example with the marbles was pretty straightforward. What I want you to do now is I want you to pause for a minute, and I want you to use what you know about quantum mechanics so far and think about what makes this example different from the example with the marbles and, frankly, weirder. So, again, take a minute, pause the video, and just think about this for a while. Hopefully you've noticed some differences. And the key difference is superposition. In the scenario with the marbles, Alice always had the red marble and Bob always had the blue marble. They didn't know who had which one because the conditions in which they were given the boxes made that or obfuscated that information, but the marbles were where they were the whole time. In fact, we can even extend this. We could say Alice and Bob took their marbles home with them, never opened their boxes. Years went by, they died, and their children inherited the boxes from them. If Alice's children open her box and find the red marble, then they would be able to say that Alice had the red marble the whole time. Alice might not have known it, but she did. Likewise, Bob's children would say that Bob had a blue marble in a box the whole time. If the children were aware of this whole experiment, they would also know that the other family had the other colored marble. If they weren't aware of this experiment, then they would have no idea about the other marble. In that case, because they didn't know the conditions in which the entangled state was created, they actually wouldn't be able to learn anything about the other state. Because in order to infer anything about the state as a whole from a measurement of just one part of it, you need to be aware of the conditions in which the entanglement was created. What we just described isn't true for the decay of the pi meson and Alice and Bob's measurements there. The reason is that Alice's electron is neither spin up or spin down until she measures it. And Bob's positron is neither spin up or spin down until Bob measures it. Unlike the marbles where Alice had the red marble and Bob had the blue marble, the electron and the positron spins are in a state of superposition until Alice or Bob measures one of them. Until a measurement is performed, the electron isn't spin up or spin down, and the positron isn't spin up or spin down, but instead they are in a superposition of states of both. So when Alice measures, for example, that the electron is spin up, she cannot say that her electron was always spin up, and that therefore Bob's was always spin down. This is a little crazy in a lot of different ways. One of the ways is this. Once again, before either elephant makes a measurement, both particles are in a superposition of states. If Alice performs a measurement of spin and finds, for example, that her particle is spin up, that means her particle is no longer in a superposition of states. She collapsed the superposition so that now there is a well-defined angular momentum of the electron in the z direction, and it's up. But that means the positron also now must have a well-defined angular momentum, and it must be down. But Alice didn't touch the positron. And in fact, the positron can be very far away from Alice. Alice might be sitting here on Earth, and Bob might be on vacation on Jupiter. And the moment Alice performs her measurement of the electron, the state of the positron is determined as well. If Bob were to then perform a measurement, Alice knows exactly what he will find. So Alice's measurement of the spin of the electron immediately, instantaneously determines the state of the spin of the positron, no matter how far away the positron is. Based off of everything that we learned about relativity, that should make you uncomfortable. In fact, it gets worse. Consider a particular reference frame in which Alice measures the spin of her particle at this particular space-time coordinate, and let's say that she finds hers once again to be spin up. And in this reference frame, perhaps Bob measures the spin of his particle and finds that it's spin down a short time later, a large distance away. But now let's consider a different reference frame, one that's moving at nearly the speed of light in the positive x direction relative to the one that we've drawn so far. Making use of what we learned about simultaneity, we can see that in this new reference frame, Bob's measurement occurs before Alice's. So which came first, the chicken or the egg? I mean, Alice's measurement or Bob's measurement? Does Alice measuring spin up determine the state of the positron that Bob then measured to be spin down in order to conserve angular momentum? Or did Bob's measurement collapse the superposition, and his measurement of spin down of the positron determined that the electron must be spin up? Or maybe we consider an intermediate reference frame where these two events occur simultaneously, where Alice and Bob simultaneously perform measurements on their particles and arrive at results consistent with conservation of energy, despite the fact that the particles they're measuring can be separated by light years and are being measured at the same exact moment in time. If not for the superposition manifest in these quantum systems, there would be no problem, because the system would have just been whatever it was, even though Alice and Bob didn't know what it was. But based on our understanding of quantum superposition, that's not how it works. The particles didn't have definite states of spin before any measurement was performed. They were in a superposition, and so they were neither spin up or spin down. And so how do they know? How do they coordinate with each other to always satisfy the condition of conservation of momentum, that they always sum to zero, if they're so far away from each other and being interacted with so close together in time that they don't have time to communicate? Right? Information only can travel at the speed of light or slower. Einstein called this behavior spooky action at a distance. And he, along with two other physicists, Podolsky and Rosen, wrote a paper, famously called the EPR paper, in which they argued that this behavior clearly is in violation of the principles of relativity, and that therefore our understanding of superposition must be incorrect, and that these particles do in fact possess definite states of spin beforehand, and our understanding of quantum mechanics was merely incomplete. A lot has happened since then, and the prevailing opinion today, and in fact for decades already, is that Einstein and his co-authors were wrong. This is in fact consistent with special relativity, and that superposition is in fact a correct description of the real world, and we have the experimental evidence to back it up, with some caveats. Next time we'll focus on how this is actually consistent with special relativity, because despite some early protests by prominent physicists like Einstein, it is actually consistent with it. There is no problem here, although it's not exactly obvious how that's the case. It turns out that the speed of light is not exactly the impenetrable barrier that we've made it out to be. Although don't get too excited, the exceptions don't allow us to do anything fun.